So welcome. We are going to be talking about inverse matrices and determinants today. Hopefully you've already downloaded the note sheet. I think it will help a little bit because that should give you the problems that you should be doing. Because remember, math is not a spectator sport. You shouldn't just be watching this video. You should be actually doing the problems along with it and then checking your answers like you would had we been in class. So I expect that that is being done. If not, then perhaps that's something that you are missing as you are going through these lessons. So hopefully you've downloaded that and are working on the problems as we go along. So the first thing we're going to talk about is inverse matrices. So in order to show that a matrix is an inverse of another matrix, you need to find the product. So in this case, you're going to multiply A times B. If you follow the procedure and you multiply A times B, you should get that matrix A is the point it is multiplied is 1, 0, and 0, 1. If you multiply B times A, you should also get the product that is 1, 0, and 0, 1. If this holds true, that guarantees that the matrices are inverses of each other. If that doesn't happen, and it has to be that specific pattern so that the ones are on the diagonal going from the upper left to the lower right, and the zeros are going the other direction from the upper right to the lower left. If that happens, then that tells me that those two matrices are inverses. The same would hold true if it was a matrix by like a 3 by 3, and if that were the case, then it would be like a 1, a 1, a 1, and then all the rest of the other numbers would be zeros in between here. So that would be a matrix of something that would be a 3 by 3 to show that they're inverses. So you're just going to multiply whichever matrix they give you. So if we're going to find an inverse, and the only matrix that we're going to be finding an inverse for is a 2 by 2. Anything else will require us to use the calculator, which we'll talk about in just a minute. So if I have matrix A, in order to find the inverse of matrix A, I will follow the procedure here. So I would multiply 1 over A times D. Notice A times D is this diagonal here. And then subtract BC, which is that diagonal there. Once I do that, I'm going to take the product of those terms and then multiply that by the matrix of D over negative C times negative B over A. So all we're doing in this case is I'm taking my A and my D and I'm flipping them from where they were located before in our original matrix, and I'm taking the B, negative B and negative C, and just changing the signs of the term that was in here and the term that was in here. So then when I go to find the actual inverse, I would actually do the multiplication of this term that's over here and multiply it by the matrix that's over there to get my answer. So here's our example. I have the inverse. I want to find the inverse of the matrix 4, 5, 7, 9. So the first thing I'm going to do is I'm going to do 1 over the product of the top and the bottom and the bottom and the top. So that means I'm going to do 1 over 36 minus 35. And then I'm going to multiply that times the matrix when I switch the 9 and the 4, and then I switch the signs of the 5 and the 7. So when I do that, I would have 1 over 1, which is where that 1 comes from, over the 9 and the 7, and negative 7 and the negative 5 and 4. So then I would multiply that by 1, which gives us the answer of that 9, negative 5, negative 7, 4. So that one's not so difficult. Here's another one. I want to find the inverse of 3, 9, and 2, 5. So again, I would do 1 over 15 minus 18, which is what I show you here. And then I've switched around the 3 and the 5 and the signs of the 9 and the 2. That doesn't really look like a 3, but oh well, that is a 3. And then from there, I would just take those numbers and I'm going to multiply them. So when I multiply the 1/3 into the parentheses, I'm going to be left with this that doesn't exactly look like that, but that's 5/3 here, negative 5/3 and 2/3, and then 3, and then negative 1. So that would be the answer that we get when we find the inverse of that 2 by 2 matrix. Now, if I look at this matrix, it is now a 3 by 3. As I said, there is a procedure for finding the inverse of that, but we will not be doing that in this class. So what I would expect you to do, depending upon which version of the operating system you have on your calculator, either you're going to go to Alpha Zoom to get a 3 by 3 matrix and enter in A to the negative 1. Once you've entered in A to the negative 1, actually A, you would just raise it to the -1 power, and that would give you the inverse of matrix A. Or if you have the older operating system, you would go into the matrix option, and in matrix A, you would, under the names, you would go into edit, and you would edit matrix A and type in the matrix that is here. And then in your home screen, the regular calculator screen, you would bring up the name of matrix A. So it would look like that. And then you would raise that to the -1st power. And when you do that, with both methods, either one that you get, you should end up with this as your inverse. Hopefully you found that. If there are any questions about how to do that on the calculator, hopefully I can answer that relatively quickly when I see you in class. But that shouldn't be too difficult. You're just finding the inverse on the calculator. And remember, anything that we do that's above a 2 by 2, I would expect you to do on the calculator. We will not be doing that in class, no matter what it says in the book. So then the next thing we're going to talk about is a determinant. So here is a determinant of how to find a matrix. To find the determinant of a 2 by 2 matrix. In a determinant, notice that the symbol here is the DET, so that tells you you're finding the determinant. Also notice that the difference between the symbols between the matrix that's here and the determinant is here is it almost looks like an absolute value, except in this case it's not. It's a determinant, so that's the notation that tells us we're finding the determinant. When I find the determinant of a 2 by 2 matrix, it looks much like what we just did for the inverse matrix. You do the top left times the bottom right, so that gives me AD, and then I subtract the bottom left times the upper right. And then I just do the math for that one because it would be numbers at this particular case. So then when I get the determinant, it's just going to be a number of some sort. Now it becomes a little bit more difficult when I have a 3 by 3 or anything else. What you have to imagine here is I'm going from this to that. In my matrix, I have my A, my D, my G, B, E, H, and then C, F, I. And there's my close of my determinant. But then over here, I also am going to be rewriting those columns again. So my A, my D, and my G go there. And then my B, my E, and my H. An H doesn't look like one, but it's an H. It goes there. So then when I go to do my determinant, I would multiply the A, the E, and the I, and then the B, the F, and the G, and the C, the D, and the H. So notice that that's where that first parenthesis comes from. I'm going to take those diagonals, I'm going to multiply down the diagonal and then add those products together. And then I'm going to go the other direction to get my other diagonal. So I would go GEC, and then HFA, and then IDB, and that's where the other parenthesis comes from. Again, I'm taking those numbers and I'm multiplying them, but then each diagonal I'm going to add together. And then I'm going to take the down diagonals, add them together, and the subtracted going up diagonals and add them together, but then subtract the difference. So that's where those multiple letters come from, by rewriting the first two columns again so that you can find the determinant. So here's an example. I'm going to be finding the determinant of this 2 by 2 matrix, which becomes relatively easy because I'm going to just take 7 times 3, which is 21, and subtract 2 times 2, which is 4. So 21 minus 4 gives me 17. So that's relatively easy. When I do this one, I'm going to have my matrix, and then you could sort of imagine that I have a 4, the 5, and the 1, and the 3, the -7, and the -2 written again. So when I go to multiply, I would multiply the 1, the -7, and the 1. Oops, sorry, I'm going the wrong direction here. My goodness. I'm doing the 4 times the -7 times the 2 to give me -56. And then the 3, the 0, and the 1 to give me 0. And then the 1, the 5, and the -2 to give me -10. So that's where that comes from. Now I go the other direction, where I multiply 1 times -7 times 1 to give me -7, and the -2 times the 0 times the 4 to give me 0, and 2, the 5, and the 3 to give me 30, which now I'm going to take the first parenthesis, and if I add those together, I would get -66, and the second parenthesis, where if I add those together, I would get 23. I sort of wrote it as plus a -23, so you get the same idea. And so -66 plus -23 is -89. So that's the value of that particular determinant. And then the last thing I could do is an application with determinants. An application with determinants is to find the area of a triangle. So if I have a triangle and the vertices are given as they are written there, I can find the determinant, which gives me the area. Notice that it's got a plus or minus here. That's basically to tell us that no matter what, the area of the triangle is going to be positive, because I can't have a negative area of a triangle. That would just be silly. So I would write the coordinates here, where my x coordinates would go in the first column, my y coordinates would go in my second column, and then there's no other coordinate there, so we're just going to put a 1 there to sort of hold the spot so that I have 3 coordinates, and because that's what the formula says to do. So then I would find the determinant of that to find the area. And that's basically what it says here with the plus or minus, because I can't have a negative area. I have to use either a positive or a negative so that it does become a positive area. So for instance, here's my triangle, and if you sort of ignore my scribble over on the side there, we can see that I have a triangle, and the coordinates are 2, 4, 5, 1, and 2, negative 2. So I would set that up by putting that into my formula. When I do that, I would have the plus or minus 1/2, so that's there, and then I would write my x coordinates in the first column, my y coordinates in the second column, and my 1s in the third column, because I don't have a third coordinate. So there's my 2, 4, 1, 5, 1, 2, and 2, negative 2, 1. It doesn't matter which order you put them in, as long as they're there. If I had put the 5, 1, 1 first, it wouldn't make a difference. From there, you would find your determinant. So you would rewrite the 2, 5, 2 and the 4, 1, 2, or 4, 1, negative 2 in the next column, multiply down from the top to the bottom, and then add the bottom to the top, and then subtract those 2 parentheses. And when I do that, the area is 9. You should see that that should be the same thing if I had done it using 1/2 base times height, because 1, 2, 3, 4, 5, 6. 6 times 1, 2, 3. 6 times 3 is 18, and 18 divided by 2 is 9. So my area becomes the same thing no matter what, whether I use the determinant or whether I use the formula that you talked about in geometry. So hopefully that's a pretty good review of what you were doing with inverse matrices. Hopefully you understand it very well, and we can talk about it in the next class. I'll see you then. Bye.